Hello. Hello, everyone. Okay, so plan for today. We are going to talk about 2D motion. We're going to talk about motion in 2D. Mostly, we're going to have some fun. Okay, mostly we're going to have experiment with different approaches. I want you to kind of get the feel for equations of motion overall and in equations of 2D motion. We will talk about modeling different things with motions. I will show you some animations, hopefully, and there will be some monkeys involved, some hunters, and a little bit of animal cruelty. So sorry about that. Okay, so let's get to it. Right. So I'm sharing my screen. So if you can't see my screen, please let me know. Last time we spoke about this, we were talking about projectile motion, and we saw different approaches. So we can change the angle. So this is an animation. We can change the angle, we can change the speed, and we can get some interesting results. So this is at 11 meters per second. This is 13 meters per second. This is 15 meters per second. So quite predictable, right? So you go further if you shoot at a higher speed. You can also change the angle. Let's say you have a fixed speed of 20 and you can change the angle. So starting from 25, 30, let's go further, 35 degrees, 40 degrees, 45 degrees, and then 50 degrees. And you can actually see now we go less of a distance, right? So if we keep increasing, so the maximum distance is at 45-degree angle. If we keep increasing the distance, we get shorter and shorter and shorter. And ultimately, of course, 90 degrees, we get, well, let's do 85 first. 85 degrees, we go really short. And with 90 degrees, we go nowhere. We literally go up and down. So what I want to do today is I want to show you how to create this. Like this is some very easy maths involved in here. Very easy programming, and I'll show you bits of it. And if you like programming, you can do it. You can do it by yourself. By the way, one thing I would recommend looking into, if you're not already doing some Python, please learn Python. This is super easy. There's literally a website. It's called Practice python.org, and it has problems. So easy ones with 1 pepper, slightly harder with 2 peppers. With 4 peppers are really complex. But and you have solutions. So it's a free to use website. Practice Python, and yeah, just get on with it. And if you need a simple online Python, it's literally called online Python. You can just create programs straight away. So like print hello world, yes, Hello world. This is something that will really make your life better in the future. Okay, and you run the code, hello world. Okay, so a very easy online Python which you can use, and practice Python is the problems that you can do. So I really recommend doing that. I myself, when I needed to learn Python, I just did this over a week or so, and now I'm a better person for it. Okay, kidding, but I'm a better programmer. Because when I was at university, I studied different. I studied Pascal, I studied C++, but I never studied Python. So it was a fun week for me. Anyways, we have this model, projectile motion. So how on earth does it work? Well, it's actually really simple. You can do very simple. You can do a model of this using Desmos. But first, we need to understand what an equation of motion is. And I'll just remind you equations of motion. So let's have a look. Pen. A simple equation of motion. Equation of motion. Imagine you are traveling along a straight line with constant speed. Straight line, constant speed. And this is your x, is your coordinate. So you start from x0, this is your initial position, and you travel along. After some time, you end up at point x. So x0 is your initial position, and x is your final position. Right. The distance that you have traveled, let's call it s, as displacement s. Well, it's very simple. You know this from perhaps primary school, that the distance traveled is equal to your speed multiplied by time. But your displacement, your position is your final position minus the initial. It's the difference between the two coordinates. So let's say you were at point 3 and now you're at point 5. You have moved 2 meters, right? So your s is actually x minus x0. It's the change in your position, equal to v multiplied by t. We can rearrange that and we get x equals x0 plus vt. Now, this is an equation of motion. Why is it an equation of motion? Because it tells you, if you know t, you know x. This is an equation of motion. Gives position at any given time. Given time. The same thing is true if you work with vectors. So literally the same stuff, but now we are moving in a straight line, not necessarily along the x-axis. So with vectors, you have s vector is equal to velocity vector multiplied by time. And s is the change in position. So it's r final position minus the initial position equal the velocity multiplied by t, where r is the radius vector, is the position vector. We call it the radius vector. And therefore r is equal to r0 plus vt. So that's moving constant speed, constant velocity, in 2D. Right. So what is that? Well, you can write it as vector r. This is also an equation of motion because it gives you the position vector at any given time. You can rewrite this as x and y equals the initial position x0, y0 is a vector plus the x component of your velocity and the y component of your velocity multiplied by time. And if you just consider the top part, it's literally x equals x0 plus vt. And the bottom part is y equals y0 plus vt. So I'll give you an example. Sorry, do you understand? On a scale of 0 to 10, how well do you understand up to this point? How well do you understand what I'm talking about? Okay. So let's R is the position. R is the position vector. R is the position vector. Please watch the previous webinar if you're not sure. Vector. Now, literally, R is a vector, and x and y are the coordinates of x and y are the coordinates of the object. Imagine, so an example. A marble roll starts at 4-3 and rolls with velocity v equals 2-1 meters per second. So what would the equation look like? Well, this is the initial position, right? This is the initial position. So this is R0 and this is V. So R is equal to R0 plus VT. So R0 is 4-3 plus VT, so 2-1 multiplied by T. This is the equation of motion. So radius vector, the position vector of the marble at any given moment of time is 4-3 plus 2-1 T. That means if you substitute T, it tells you the position of the marble. Confused.com. Let's rewrite this. Rewrite this as xy equals 4-3 plus 2-1 t. From here, we get x is equal to 4 plus 2t, and y is 3 plus 1t. 3 plus t. This is literally the same thing. So this and this are equivalent. Let's see what happens. Let's model this. So Desmos is a very powerful tool. So I'm going to model this. I'm going to say, so the coordinates of the object are x is 4 plus 2t and y is 3 plus t. So we can say that the coordinates are 4 plus 2t, comma, 3 plus t, because this is x and this is y. So let's plug this in. So we want a point with coordinates 4 plus 2t, comma, 2 plus T. Three plus T. Okay. And let's label it marble. And T changes from 0 to, let's say, 6 with a step of 0.5 seconds. Right. So what do we see? We see that the marble, when T is okay, never mind. Marble. When T is 0, the marble is at 4.3. And that makes sense. If you substitute T0, it's 4.3. 1 second later, the marble is now at 6.4. 2 seconds later, the marble is at 8.5. You can see that the marble moves as time goes by. The beautiful thing about it, this tells you the position of the marble at any given time. So if you know the time, you know where the marble is. Does that make sense? Do you understand what I've just done? On a scale of 0 to 10, please. Yeah. Any questions? And the vector with coordinates 4 plus 2t and 3 plus t is known as the position vector. The position vector is simply a vector drawn from the origin to the position of the marble. So as time goes by, the marble moves, and that makes perfect sense. We can add another marble. Let's have a marble that starts with starts at position 7, comma 8, and moves with velocity minus 3, comma minus 1. Multiplied by t. Ooh, interesting. I can actually do it like this. Marble 2. Marble 2. And this is marble 1. I can see as time goes by, both marbles move. Okay, they don't really intersect. Let's change the initial position of marble 2. It's going to be, let's say, 12, 0, 0 minus 1 plus 1. Let's see if this works. So you can see that the marbles won't collide, but we could adjust it so that they do. Ah, yeah, they are. They come really close to each other. Okay. Let's do one of the questions from the assignment. Heroic Hank and Dodgy Dave. You remember this question from the assignment? All right. Right, so we don't know L. We don't really know L. I don't think they give us L. Okay. Well, we have Dave and Hank. So Dave is the red one and Hank is the blue one. Okay? And then we have the equation of motion, and we have the angles? Theta. Oh, we don't know the angle. Okay. And this one is 30 degrees. Okay, so let's write the equation for Dave. And I'm going to do this. Okay, let's label it Dave, and label this Hank. And Dave has equation of motion. So we literally put, so L, we don't know L, but let's assume it's, oh, we really don't know L, but let's make it what, 20. 0 plus, now alpha is 30, so V1 is 10. Now 10, so it's 10, oh, sorry, minus 10 multiplied by cos 30 degrees, because he's comma 10 multiplied by sine 30 degrees and multiplied by time. And Hank starts from 0, 0 plus V2. V2 is 15. So 15 multiplied by cos theta and 15 multiplied by sine theta. Doesn't like it. Okay, let's make the angle K. And K. And the K can take values from 0 to 90 degrees with a step of, well, let's wait, 1 degree. Okay, so let's see what we have so far. Let's see if we have any luck. So we have Hank and Dave. They're here. Let's change the angle. This is the angle, and let's make Hank at 30 degrees as well. Let's see. Okay, too sensitive. 0.05 and 2 seconds. Why are they running downwards? Doesn't. Oh, okay. We are not in degrees, of course. We are in radians. We need to be in degrees. Okay, that makes more sense. Let's see. Okay. Now they're running. No, they're not reaching each other. So you can see that Hank will not catch up with Dave. They miss each other. Okay, let's change the angle. Looks like it has to be smaller. Ooh, that's closer. So you see what I'm doing? I'm modeling this. So I'm literally just typing this in, and you can see what's going on. Hank and Dave. So you can practice this. You know what? I'll share this with you. I'll share this with you so you can play around with it. And yeah, get some interesting stuff going on. Okay, so but you can change the angle again. But ultimately, what's going to happen is like they have to meet, so they have to have the same coordinate. They have to have the same vertical component. So it doesn't matter how they're moving horizontally, as long as they are moving, we want Hank and Dave to move the same distance vertically. If we want Hank to meet Dave, his vertical velocity has to be the same as Dave's vertical velocity. And we look at this and we see that if we split Hank's velocity and Dave's velocity into components, this is called V2y and V1y. This is the vertical component, the y component. So V1y has to equal to V2y, because only then, only if they are traveling at the same vertical speed, that means they will have the same y coordinates. When they meet, they have to have the same y coordinates. And because they start from the horizontal position, they have to meet at the same y coordinate. And that means they have to have the same vertical speed. And therefore, V1y, which is V1 sine 30, is equal to V2 sine theta. And sine theta is V1, which is 10 multiplied by sine 30 divided by 15. So theta is something arc sine of this 10 times sine 30 divided by 15, which is arc sine 1/3, which is approximately arc sine 1/3, 19.47 degrees. 19.47 degrees. Let's check that. Go back to our model. If we change the angle to 19.5 degrees, 0.5. Let's see, Hank and Dave start, and bam, 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 bam. You can see that vertically they travel the same distance, and well, it's not sensitive enough. Step, let's make it 0.01, and from 0 to 1, you can Hank and Dave move, and they do meet if the angle is 19.5 degrees. So I'm just playing around with it at the moment. Yes, I'm just showing you the link. And if you were to create a program, for example, like on Python, if you wish, you could make it work once you know the math behind it, and physics behind it. Okay, so now let's do the same, but now let's introduce gravity. Let's introduce gravity. Let's model. Let's model the projectiles. So what I'm gonna interesting. Hank started moving. They're moving. Anyways, let's do another one. And this time we're going to model the projectiles. And, well, modeling with 2D motion, radius vector. And so how can we model this? How can we model this? Well, we need the equation of motion. So horizontally, we know that horizontally it is horizontally it is constant velocity. Yeah, so the projectile horizontally. Oh, I accidentally sent it as a direct message. This is the Desmos I was using, so you can play around with it. Okay, now here there are two different approaches. Well, you can say that horizontally you have constant velocity. Horizontally, constant velocity. And that means x is equal to x0 plus v, x, the horizontal velocity, multiplied by time. Vertically, we have a constant acceleration. In other words, it's suvat. And I'm just going to take the suvat equation. S is equal to ut plus 1/2 at squared. Now we know that S is the change in position. So that's y minus y0. That's the change in vertical position. U is the y velocity multiplied by t, time, plus 1/2 g t squared. But we already know that g is minus 10. So we can write that y is equal to y0 plus vyt plus 1/2 gt squared. Okay, well, what do we also need? We also need that Vx, the horizontal velocity. So if we shoot at an angle, so let's say we shoot at an angle at velocity v, and the Vx is v cos theta, and Vy, we already know that, Vy is v sine theta. So we can rewrite this formula. So x is x0, the initial position, plus vx, so that means v cos theta multiplied by t, and y is equal to y0 plus v sine theta t plus 1/2 gt squared. Okay. This is a general equation of any projectile. This works for any projectile. So let's say we are shooting at an angle. So let's do a specific example. So 60 degrees, 20 meters per second. Okay. Example one. Theta is 60 degrees. Velocity is 20 meters per second. And your initial position, x0, y0, is 0, 0. So you start from 0, 0, because this is the y-axis, and this is the x-axis. X-axis, y-axis. Okay, so you're shooting a projectile. It goes like this. So let's write down the equation. Let's write down the equation of motion. So x is equal to x0 plus v sine theta t, and y is y0 plus v cos. Oh, that's cos. Sorry, that's sine theta t plus 1/2 gt squared. So this is going to be x is equal to x0, which is 0, plus v, which is 20, multiplied by cos 60. Cos 60 is 1/2, so multiplied by 1/2, multiplied by t, which is 10t. Y is y0, so 0 plus v, which is 20, multiplied by sine theta, so that's square root of 3 over 2t, minus, because this g is minus 10, so 1/2 times 5, so it's minus 5t squared. And we can simplify this as 10 square root 3t minus 5t squared. Let's see where this takes us. So I'm gonna go to need another one. Okay, so it is 10t zero to 3.02 10t, comma 10 square root 3 multiplied by t minus 5t squared. And let's label this as the ball. Okay, so when t is 0, the ball is here. So let's see. And as a matter of fact, what I'll do is I'll just make a trace. I don't like that. Let's see if we can get something. Ooh. I don't want a slider. Okay. And yes. What if I do this? Yes, finally. Ball. Right. So here's the ball. And it's supposed to land. It's supposed to land at about 35 meters. So let's check if that is the case. So 35, we'll need 35. 35. It should go to a, it should take us about 3.5 seconds. So let's change the time. Let's make sure that we have enough time. Okay, we need 3.6 seconds. And play once. Fingers crossed. Let's see if we can make it. Bam. Okay, we did it. We did it. We made the same model. Okay, we took slightly more time. Of course, it can't go underground, but that's it. That's what we did. We managed to create a model using Desmo. It's very simple, a very simple model. So I'm going to share this with you as well, so you can play around with it. I hope you're enjoying this, because if you're finding this boring, I don't know. I honestly find it so fascinating. Partly because I used to design a computer game. It was something something in the something. It was a mixture between Angry Birds and this rally car that hill climb racing. Yes, hill climb racing. I used to design a game, but it never shot. It never. We never actually released it. Wasn't very good. But yeah, I remember doing the maths, and it was quite fascinating. So you can play around this with it. Is this? Oh, what are we talking about? Vishaka, the line y equals x. It's not x square root 3. It's 10 square root 3 times t. Oh, yeah, I'm not sure exactly what you're asking. Now, so we're shooting ball. Now, let's see if we can model the ball traveling just at a 0-degree angle. So it's vertically up. So what do we change? Well, we change the horizontal velocity. Horizontal velocity becomes 0. And the vertical velocity becomes 20. 20. And same thing here, 0. And this becomes 20. And right, so we need more time, I'm guessing. So 5 seconds should do it. Let's shoot. Bam. It reaches about 20 meters and then falls back down. Let's see if this does the same thing. Reaches about 20 meters. Yeah, reaches about 20 meters and then falls back down. It's quite cool. So yeah, you can play around with this. Okay, so finally, we're getting somewhere. So we've managed to write down the equation of motion. Why the equation of motion is so important? Well, it gives you the position at any given moment in time. That's the purpose of the whole topic of mechanics. If you ask, what is mechanics all about? It's about telling you where things are at any given time, so you can make predictions. Where is that used? Well, astronomy, for example. Let's do another example. It's off the top of my head. I'll try to make it quick, but let's say we have the sun. Let's put the sun at 0, 0, 0, 0, and let's label it the sun. Sun. And then we can make a planet. So the planet will go like 4 multiplied by sine t, comma 4 cos t. And time goes from 0 to, let's say, 10,000 with a step of 5. Table, planet. Okay, let's play. It's a bit fast. Okay, degrees. Doesn't like it. Okay, let's change the time to 10 with a step of 0.01. Okay, that's better. So you can see planet. Doesn't make any sense. 1,000. That's too fast. 0.02. Okay, well, sort of. So you can have a planet going around the sun. And this gives you the position of the planet at any given moment in time. If you're in 2D, of course. Oh, yes, for sure. You can rearrange to interpret X, but we're talking about, yeah, you can write the equation in terms of Y in terms of X, of course. But we're talking about X and Y in terms of T. This is the point I'm trying to make. This is the radius vector or the position vector. Right. So another example of 2D motion, right? So this is circular motion. There's a planet going around the sun. You can have a. Well, I'll share this with you, and my challenge to you is: can you make a moon? Can you program a moon going around the planet? Anyways, it's actually not that hard if you think about it. You just need to add. Well, okay, that's my challenge to you. Make a moon. Make a moon using the same method. Now, the monkey and the hunter, finally. The monkey and the hunter. So the legend or the story goes as such. A hunter is trying to shoot a monkey for whatever reason. I don't know. Animal cruelty, as promised in the beginning of this webinar. Trying to shoot a monkey. The monkey sees that and decides that if at the moment when the hunter pulls the trigger, I let go of the branch, the bullet will go past. The bullet will. So the hunter is aiming at the monkey. The monkey sees the shot and immediately releases her hands and starts falling down. What would happen? Would the bullet go over Does it depend on the bullet's speed? What's going to happen? Well, we can model this. We can model this, and thanks to this. I'm going to make a simple model first. Let's go back to which one? Let's make another one. Why not? We're going to have a monkey. So at position 20, let's make it 14, comma 8 minus 5t squared. Zero to a 0 to 4, the step of 0 0.2. Okay, so the monkey is here. We are going to copy that. This is the monkey. Right, so let's see what happens with the monkey when I press play. The monkey falls down. Once again. So it takes about 1.5 seconds. The monkey to fall. Okay, so the monkey falls. Let's say the hunter is at the same height, at the same level, and it's shooting the hunter is shooting horizontally. And so we have the bullet. And it is at 0. And it's moving with, well, let's say it needs to travel about 10 meters per second. 10 meters a second. 10t. And okay. And okay, here's the bullet, here's the monkey. Now, let's say we switch off gravity. There's no gravity. And so I'm just going to change this to 0. Because gravity is 5. It's a half times g. And let's see what happens. The bullet, it's like easy. Okay. So now let's switch on gravity. Interesting. I wonder what's going to happen. So you can see that with gravity, because the monkey and the bullet, they experience the same gravity. And you can see that they will meet. unfortunately for the monkey. So let's look at that. And that's if you throw horizontally. So if you see the monkey right in front of you, you're aiming at the monkey releases, you shoot, and they go. They actually, there's a good video on this. I wonder if I can find it. Monkey, and the hunter, quantum boffin. Here it is. So this is the bullet. This is the monkey. It's a quick release system. As you can see, it does hit. Does hit the target. Right. So yeah. What if we shoot at an angle? So once again, we have a bullet in the monkey. So bullet is shot from here. The monkey is here. We are shooting at an angle. So let's say we switch off gravity again. Switch off gravity. Right. So step 0.02. Animation. And you can see that the bullet hits the monkey. So just straightforward. So we are aiming. So what this tells us, we're aiming the bullet directly at the monkey. But there's no gravity, so the bullet hits the monkey. Now switch on the gravity. So we only need like 0.7 seconds. 0.7, 0.7, and with a step of 0.05. Let's see if that gives us a better, yeah. Okay. Now I'm switching on gravity back on. And let's see what will happen. And press play. So even if you shoot at an angle, it's still the same. You can clearly see that they meet. And let's what if that is a fluke? Let's try shooting faster. Let's let the bullet go faster. So where's the bullet? The bullet is this one. I'm going to double the speed of the bullet. 20. I've doubled the speed of the bullet. And you can see that they meet just earlier. The monkey would only have fallen just a tiny bit. Let's see if we can change the. Well, we can't change the angle because we have to change the position of if we change the angle, of course the bullet would miss, but we need to aim. The initial angle has to be directed at the monkey. As long as that's true, then it works. Let's try reducing the speed of the bullet quite significantly. So Let's reduce it to 5. 2.5, 5, 2.5, 2.5. Right. So we'll need more time. So it's traveling at 5, so will need at least we'll need about 2 seconds to reach the monkey. Well, not 2, 1.2 seconds. You need 1.3 seconds. Okay. Let's see what happens. Of course, that would imply that there is space to. Yeah, it can't go. It can't go under, of course. But I mean, the model works. I mean, if the bullet can't travel more than 2.5 meters, that's not a very good gun, is it? Of course, they will meet. They will meet underground. Like, I mean, the model predicts that they will meet underground, but then the model doesn't work after you hit the ground, of course. So yeah, so okay, you can change the height. You can add some height. So we need what, extra 4 meters. So let's add 4 meters to everyone. Plus 4, plus 4, plus 4. So they start slightly higher. So the bullet starts at 4 meters, the monkey starts at 7 meters above the ground, and then you can see that they will meet. They will meet here. Okay. The ground specifically. Yeah, we can assume that the bullet is made of a neutrino. The bullet is a neutrino, and neutrinos can travel through the planet Earth undeflected. They just go straight through. Yeah. You're, by the way, if you don't know about neutrinos, you're constantly bombarded from the sun. There's trillions and trillions of neutrinos passing through your body, passing through the planet Earth every second, which is quite fascinating. It's particles that are very difficult to detect. We know they're there because the standard model predicted the neutrino, and also the results of the beta decay predicted the existence of neutrinos, and they were discovered like 20 years after they were predicted, because they're so hard to detect. But we did yeah, we're not. I'm not. The point of this exercise is not to kill monkeys. It's to to learn some modeling. Right. So yeah. So we've done this. We're done shooting at an angle, and let's then do some some questions from the assignment, some similar questions from the assignment. So we had example 5. We need to find the maximum height and the maximum range. Would you like me to go through this problem? Yes or no? Just simple. Would you like me to go through example 5 from the assignment? Okay. Yeah, fine. Right, so for this question, you start at 0, 0. Then you want to find this point. You want to find this where this is. You want to find the maximum height. And what the angle for which the range is maximized. The angle for which the range is maximized. Okay, that's fine. Right, so we'll find the duration of the flight first. What the first thing that we do, we separate the velocity into components. We have the horizontal component of the velocity, and we have the vertical component of the velocity. So this is going to be V0 cos theta, and this is going to be V0 sine theta. We split the movement into horizontal and vertical. We say vertical motion is suvat. So for this vertical motion, we start from here, we finish here. The vertical displacement, is 0 because we haven't moved up or down. We finish where we started in terms of vertical motion. Because vertically it looks like this. Wow. We finished where we started. Initial velocity is V0 sine theta. Final velocity, we don't know. We don't really need to know. Acceleration is minus g, and time, well, time is what we need to find. So we need an equation that does not contain v, and we know that equation. S is equal to ut plus 1/2 at squared. And this is a Suvat equation without v. And we substitute everything. So 0 equals u, so it's v0 sine theta t minus 1/2 gt squared. Rearranging, so we have 1/2 gt squared equals v0 sine theta t. We can divide by t. We are allowed to divide by t because t is not 0. So t is not 0. Of course, the duration of the flight is not 0. Therefore, we can divide by t. So 1/2 gt is equal to v0 sine theta. So t is equal to 2 v0 sine theta divided by g. This is the time of the flight. Now, the range of the projectile is how far you travel. It's how far you travel. And now we need to consider the horizontal motion. Horizontal motion. It's a constant speed. Constant speed. That means S is equal to Vxt. So the displacement, L, is equal to the horizontal velocity, which is V0 cos theta, multiplied by time. But we already know time. Time is 2v0 sine theta over g. So we substitute that in. We have v0 multiplied by cos theta multiplied by 2v0 sine theta divided by g. And we can simplify that. So this is V0 squared multiplied by sine theta times 2 times sine theta. So 2 times cos theta times sine theta. Can anyone recognize this formula? No, not equals to 1. It's sine 2 theta. It's V0 squared multiplied by sine 2 theta divided by G. And that's the formula. L is equal to V0 squared sine 2 theta divided by G. Okay, let's analyze this. When is the range maximum? Well, V0 squared is fixed. Sine 2 theta. Well, sine, we know that sine is between -1 and 1. So the range maximized when this is as big as it can get. And the V0 squared is fixed, G is fixed. So sine 2 theta is 1. Because that's how big sine can get. Sine can only be up to 1. Therefore, if sine 2 theta is equal to 1, well, 2 theta is arc sine 1, which is 90 degrees. So 2 theta is 90 degrees. Theta is 45 degrees. Range is always maximized at 45 degrees if you're shooting from the ground and there's no air resistance. Shooting maximum when shooting from the ground and with no air resistance. Because if you are not shooting from the ground, let's do an experiment. Let's say we're shooting from 10. So I kind of get the feeling, okay, let's go slower. All right, okay. So 10, 20, so 0, 20. 30. 40. Wow, look at that. And 45, I'm guessing it's going to be less. You can see that at 45 gives you a smaller distance than 30. It looks like the optimum is around 30. 30, let's say 32. Nope. 31. Nope. 29. Not much of a difference. So somewhere around 30. Okay, so yeah, there's no strict rule where when you're not shooting from the ground. If you're shooting from the ground, then it is 45 degrees. And if you do any other angle, it's going to be less. Okay. Sorry. That's for the proof. Now with air resistance, there's an interesting story. Like in I think it was World War One. Germans designed a very powerful gun to shoot shells at very long distances, like 100 miles-ish range. And they started experiment. They all obviously knew that 45 degrees gives you the maximum range, but some German guy just said, "Well, why don't we try shooting at 70 degrees?" And they tried 70, and it was further. It was further than 45. What happened is because the 70-degree projectile went out of the thick layers, it went into the thin atmosphere where there's very little air resistance. So it very quickly left the thick layers of atmosphere, it went into the stratosphere, well, or at least above 10 kilometers, and it managed to travel much, much further. So there was like a huge increase of range just by firing at 70 degrees. So they figured out that they can get a bigger range with 70 degrees. But this is a whole other story. And involves wars, which I'm not particularly keen on, especially with one going on right now. So yeah, that is uh, that is uh, that is that. I just wanted to say a few words, not to overload you with information. But when you're shooting at a projectile like this, what do you do? Well, there are different options. Of course, you can model this by all means. Another way of approaching this, you can say, okay, so what we've done here in the assignment, we said that this is the x-axis. This is the x-axis, and this is the y-axis. We found the equation of this line. We found the equation of this slant line. The equation of this slant line is y equals minus x tan alpha. That's the equation of this line. And we found the equation of this line, and we found where they intersect, where the two lines intersect. That's one way of doing it. Another way of doing it would be to direct the x-axis can direct the x-axis like this. This is the x-axis. This is the y-axis. The y-axis. Right. Now you have the acceleration. Acceleration is downwards. This is g. And yeah, you're shooting at an angle of alpha. So let's take this, take a snapshot and twist it. This is a common practice. So this is advanced stuff. So don't worry if you don't fully understand it. So I'm twisting this. And now I can see that we have the x-axis going horizontally, the y-axis vertically, but the acceleration now has two components. The acceleration has a downwards component and a horizontal component. And this is going to be g sine theta, and this is g cos theta. Now, that means it is accelerating horizontally and accelerating vertically. But that still works. We can write the equation r is equal to r0 plus v0t plus 1/2 gt squared. Well, okay, not t squared, gt squared, but 1/2 at squared. And now x, y, we're going to rewrite this, is equal to x0, y0, that's 0, 0, that's easy, plus v0. Now we can split the velocity into components. This is v0 cos theta and v0 sine theta. So v0 cos theta, v0 sine theta multiplied by t plus 1/2. Now acceleration, the horizontal acceleration is g sine theta, g sine theta, g, and the vertical g cos theta. Oh, vertical is minus, so it's minus g cos theta and t squared. Now you got the equation. You got the equation of the you got x is equal to v0 cos theta t plus 1/2 g sine theta t squared. This is the x coordinate, and the y coordinate is v0 sine theta t minus 1/2 g cos theta t squared. Once again, this is really advanced stuff, so don't worry if you get lost. Hopefully some of you will get it. It could be different, of course, but we are shooting horizontally. That's why it's different. So if we were shooting like this, it would be different. But that's no. We are the angle is the same. It's alpha, not theta. But okay, never mind. So we need to solve. We need to solve for y equals 0 because we finish. We're at a point where y equals 0. We finish at a point P, which has coordinates L, 0. Right? So y is 0, and that means that we, well, either t is 0, which is not possible, so we divide by t. So v0 sine theta t is minus 1/2 g cos theta t squared equals 0. So either t is 0, or v0 sine theta is equal to 1/2 g cos theta t. In other words, t is equal to 2 v0 tan, well, sine theta divided by g cos theta. So 2 v0 divided by g tan theta. So it's quite cool. So this is the time. And then you substitute the time in. So t is 2 v0 divided by g tan theta. You substitute the time into here to find L. And this is L is equal to v0 cos theta t, which is 2 v0 divided by g tan theta plus 1/2 g sine theta multiplied by 4v0 squared divided by g squared tan squared theta. Okay, this got messy very quickly, but let's see if we can simplify this a little bit. So the range, the distance traveled, is 2v0 squared divided by g multiplied by tan times cos, tan theta, cos theta, plus 2 cancels, g cancels, so 2v0 squared divided by g sine theta tan squared theta. So we can take 2v0 squared divided by g tan theta, open bracket, cos theta plus sine theta tan theta. I don't think we need to simplify any further. And what is the answer, by the way? Does that come even close? Oh, so we found t, which is 2v0 tan theta over g. So that is correct. And the distance is 2v0 sine. Interesting. They have a slightly different answer. 2v0 divided by sine theta, sine alpha. Oh, yeah, you can. I think you can simplify that. Tan theta is sine over cos, so it's cos theta plus sine theta times sine theta over cos theta. You can multiply this both sides, so this is cos squared theta over cos theta. So it's 1 over cos theta. Aha! So this is going to be 2v0 squared g tan theta multiplied by 1 over cos theta, which is, and tan is sine over cos, so it's going to be 2v0 squared sine theta over g cos squared theta, which is the same answer as before. So I've done it in a different way. It's a completely different approach. So I've had the x-axis along the slope, y-axis perpendicular to the slope, and I did a different equation of. So yeah. So hopefully you got some interesting stuff out of today. By all means, don't worry if you've missed the last bit. If last bit was too hard, it is, because it is. Yet like this I'll tell you that a typical year 13 won't be able to do this. Like what I've just done, a typical year 13 is not. This is out of the scope of a year 13 a typical year 13 student. Maybe top year 13 student, yes, but not and not even the middle top. So don't worry. Enjoy your week. Enjoy finishing the assignment. And yeah, see you in a week. I like I hope you like them. See you.